Tonight, we roll into a different kind of journey, not across state lines or through mountain passes, but beneath the hood and under the chassis, into the world that keeps 18 wheels turning, pistons firing, and air brakes holding strong against gravity on those long mountain descents. This is the realm of maintenance, where oil meets metal, where small decisions made in truck stops and service bays determine whether you make your delivery or call for a tow. It is a world of rhythms and rituals, of fluids and filters, of things that wear down and things that must be rebuilt. Every trucker knows this truth. The open road is only as reliable as the machine beneath you. Tonight, we explore 100 facts about truck maintenance. Some will be familiar, spoken in the shorthand of the shop. Others might surprise you, revealing the hidden complexities of these rolling giants. From the engine's heartbeat to the brake's final word, from tires that kiss asphalt to electrical systems that think faster than you can react, we will wander through it all. If you enjoy these journeys down America's highways, feel free to like and subscribe, or share a thought in the comments below. It helps others find their way here too, one story at a time. But for now, let us begin. Let us talk about what it takes to keep a truck alive. Engine oil is the lifeblood of every diesel truck. It flows through channels and passages like rivers through canyons, carrying heat away, cushioning metal against metal, suspending dirt and carbon until the filter can catch them. Without oil, an engine would seize in minutes, metal welding to metal in a catastrophic embrace. The average semi-truck requires an oil change every 25,000 miles, though this number tells only part of the story. Some trucks running long-haul highway routes with synthetic oils can stretch that interval to 50,000 miles, or even 60,000 when paired with regular oil analysis. Others, working in stop-and-go city traffic or dusty construction sites, might need fresh oil every 15,000 miles. The oil change interval is not a fixed commandment, but a negotiation between your driving style, your engine's design, and the world through which you travel. Modern diesel engines hold between 10 and 15 gallons of oil. To put that in perspective, that is enough to fill more than 20 standard oil bottles you would buy at an auto parts store. This massive volume serves massive demands. These engines generate tremendous heat, operate under constant pressure, and must perform reliably for hundreds of thousands of miles. The oil must withstand all of it. Synthetic oils have revolutionized the industry, offering superior protection at temperature extremes, better resistance to breakdown, and longer service intervals. They cost more upfront, but over the life of an engine, they often pay for themselves in extended drain intervals and reduced wear. Some fleets swear by them. Others stick with conventional oils and shorter intervals, preferring the rhythm of more frequent maintenance. Oil analysis is the crystal ball of maintenance. By sending a sample of used oil to a laboratory, you can see inside your engine without removing a single bolt. The lab measures metal particles, checking for elevated levels of iron, aluminum, copper, or chromium. Each metal tells a story. Iron suggests cylinder wear. Copper might point to bearing degradation. Silicon indicates dust infiltration. The lab also measures the oil's remaining protective additives and its contamination levels. Armed with this information, you can predict failures before they happen, extending oil changes when safe and catching problems while they are still whispers instead of screams. Many over-the-road drivers running modern equipment have their oil analyzed every 20,000 miles, using the results to fine-tune their maintenance schedules. It is preventive medicine for engines, and it works. Oil filters are the kidneys of the engine, constantly cleaning the blood as it circulates. A truck's oil filter captures particles as small as 25 to 30 microns, trapping carbon, metal shavings, and dust before they can score cylinder walls or clog passages. Most trucks use spin-on filters that thread directly onto the engine block, making replacement quick and straightforward. Some older or specialized engines use cartridge-style filters where you replace only the paper element, reducing waste. The filter should be changed with every oil change, without exception. A clogged filter will force oil through a bypass valve, allowing unfiltered oil to circulate through the engine. This protects against oil starvation but means contaminants are free to cause damage. It is a failsafe, not a solution. The oil pressure gauge on your dashboard is more than decoration. It is your early warning system, the canary in the coal mine. Normal oil pressure varies by engine, but typically runs between 40 and 60 pounds per square inch at highway speeds, dropping to around 20 psi at idle. Low oil pressure can indicate a failing oil pump, worn bearings, or simply low oil level. High pressure might suggest a clogged filter or a faulty pressure relief valve. Either extreme demands attention. Driving with low oil pressure, even for a few miles, can destroy an engine. The metal surfaces need that pressurized film of oil between them. Without it, friction generates heat, heat causes expansion, and expansion leads to seizure. Many experienced drivers check their oil pressure as routinely as they check their mirrors, glancing at the gauge every few minutes, looking for any deviation from normal. Engine oil degrades over time even when the truck sits idle. Moisture accumulates, additives break down, and the oil begins to oxidize. This is why time-based oil changes exist alongside mileage-based intervals. Even if you have not driven 25,000 miles, most manufacturers recommend changing oil at least once a year. For trucks that see sporadic use or spend months parked, this annual change is insurance against corrosion and sludge formation. Oil is cheap compared to engines. This is the math that guides every maintenance decision in trucking. Air is the invisible force that stops a loaded truck. Unlike cars, which use hydraulic brakes, most semi-trucks rely on compressed air to apply braking force. The system is elegant in its redundancy and powerful in its application. An air compressor driven by the engine builds pressure, storing it in reservoirs until needed. When you press the brake pedal, you release air into brake chambers, which push rods that rotate slack adjusters, which turn brake cams, which force brake shoes against drums. It is a chain of mechanical advantage, multiplying your foot's pressure into tons of stopping force. The entire system typically operates between 90 and 125 psi, with governors cutting in and out to maintain that range. If pressure drops below 60 psi, warning buzzers sound and lights flash. Below that threshold, braking becomes unreliable and the law prohibits operation. The air compressor is the heart of this system, a pump that breathes in atmospheric air and exhales it at high pressure. Compressors can be gear-driven, belt-driven, or cam-driven, depending on engine design. They cycle on when pressure drops below the cut-in point, typically around 90 psi, and cycle off when pressure reaches the cut-out point, usually around 120 psi. This cycling is normal and constant. What is not normal is a compressor that runs continuously, never building enough pressure to cut out. That suggests a massive air leak somewhere in the system, a failing compressor, or a stuck-open governor. Any of these scenarios can strand you at the roadside, waiting for a mechanic. Air dryers are the unsung heroes of the brake system, removing moisture from compressed air before it reaches the reservoirs and brake components. Water in air lines is a menace. In winter, it freezes, blocking passages and rendering brakes useless. In summer, it promotes corrosion, eating away at the interior of tanks and valves. The air dryer uses desiccant cartridges to absorb moisture, automatically purging collected water every few minutes with a sharp hiss. That sound, familiar to anyone who has stood near a parked truck, is the dryer doing its job. The desiccant cartridge should be replaced annually or according to manufacturer specifications, more often in humid climates, or if the truck operates in wet conditions frequently. A failing air dryer reveals itself through water in the air system, rusty air tank drains, or frost on airlines in winter. Air tanks store the compressed air, providing reserve capacity for braking even when the compressor is not running. Most trucks have multiple tanks: a wet tank that receives air directly from the compressor and catches most of the moisture, and dry tanks that supply the brakes and accessories. The wet tank should be drained daily, releasing any accumulated water and oil that made it past the dryer. Many modern trucks have automatic drain valves that do this electronically, but older trucks require manual draining. It takes only a few seconds and prevents a world of problems. Drain the wet tank, and if water or oil comes out, you know the air dryer needs attention. If rust-colored water pours out, your tanks may be corroding from the inside, a more serious issue that requires inspection. Brake chamber size matters more than most people realize. Chambers are rated by their effective diaphragm area in square inches, with larger chambers producing more force. A size 30 chamber, common on drive and trailer axles, has a 30 square inch diaphragm. Steer axle chambers are typically smaller, sizes 16 to 20, matching the reduced braking force needed on the front. Mismatched chambers can create brake imbalance, causing the truck to pull to one side during braking or leading to premature brake wear. During inspections, technicians verify chamber sizes match specifications and measure pushrod stroke to ensure brakes are properly adjusted. Stroke is the distance the pushrod travels when air is applied. Too much stroke means the brakes are out of adjustment, reducing braking power and potentially putting the truck out of service during a roadside inspection. Automatic slack adjusters were mandated on new trucks in the 1990s and revolutionized brake maintenance. Before their arrival, manual slack adjusters required regular adjustment as brake linings wore, a task that was often neglected until brakes were dangerously out of adjustment. Automatic slack adjusters compensate for wear on their own, maintaining proper stroke without driver intervention. But automatic does not mean maintenance-free. These adjusters still require lubrication, inspection, and occasional replacement. The key rule is simple: never manually adjust an automatic slack adjuster except during initial installation or brake reline. If an automatic adjuster is not maintaining proper stroke, something is wrong with the adjuster itself or with the foundation brake. An adjustment will only mask the problem temporarily. Diagnosis and repair are required, not a wrench and false confidence. Brake linings are consumables, wearing away with every application, their friction material sacrificing itself to convert kinetic energy into heat. When linings wear down to 1/4 inch thickness at their thinnest point, they must be replaced. Most modern linings have wear indicators, grooves or notches machined into the friction surface that disappear as the lining wears. When the indicator is gone, the lining is done. Brake inspection should happen at every service interval, with thickness measured using a gauge or careful visual assessment. Linings wear unevenly, with the leading edge often wearing faster than the trailing edge, so measurements should check multiple points. Worn linings are not just a maintenance issue, but a safety and legal one. Commercial vehicle inspections measure lining thickness, and anything below the minimum triggers an out-of-service violation, grounding the truck until repairs are made. Drum brakes remain the standard on most heavy trucks, despite the increasing popularity of disc brakes. The drum brake system is time-tested, durable, and relatively inexpensive to maintain. Brake shoes lined with friction material press outward against the inner surface of a rotating drum, using friction to slow the wheel. Heat is the enemy here. Excessive braking, such as riding the brakes down a long mountain grade, can heat drums to the point where they expand beyond the reach of the brake shoes, causing brake fade. At extreme temperatures, drums can even crack or warp. This is why smart drivers use engine brakes and transmission gear selection to control speed on downgrades, saving the service brakes for final stops and emergencies. Brake fade is the terrifying condition where brakes lose effectiveness, due to overheating. It typically happens on long descents when drivers rely too heavily on the brake pedal. As the brake drums heat up, they expand, increasing the distance the brake shoes must travel. At the same time, the friction material's properties change with heat, becoming less effective. The result is a brake pedal that requires increasing pressure to produce decreasing results. In extreme cases, brakes can fade to the point of uselessness, leaving a heavy truck with no way to slow except prayer and physics. Preventing brake fade requires using engine brakes, selecting lower gears before descents, and using stab braking techniques that allow brief cooling intervals. Experienced mountain drivers know these techniques by instinct, their right foot barely touching the brake pedal as the engine and transmission do the work. Air disc brakes are gaining ground in the industry, offering several advantages over drum brakes. Discs provide better performance in wet conditions because water can be squeezed out from between the pad and rotor more easily than from inside a drum. They generate less heat buildup and dissipate it more quickly, reducing the risk of fade. They also wear more evenly and are easier to inspect since pads are visible without disassembling the wheel. The downsides are higher initial cost and, in some cases, more expensive replacement parts. Fleets operating in mountainous regions or wet climates increasingly specify disc brakes on steer and sometimes drive axles, accepting the higher cost for the performance and safety benefits. As disc brake technology matures and prices come down, they will likely become the industry standard. But for now, drums remain king on most heavy trucks. The brake inspection process follows a systematic checklist, examining each component for wear, damage, and proper function. Inspectors look for cracked drums, glazed linings, leaking wheel seals, loose or damaged chambers, worn pushrods, and improperly adjusted brakes. They measure lining thickness, test chamber operation, check air lines for leaks, and verify that all components are securely mounted. A comprehensive brake inspection can take an hour or more per vehicle, but it is time well spent. Brake violations are the #1 cause of vehicles being placed out of service during roadside inspections, accounting for nearly 40% of all mechanical violations. Staying ahead of brake wear and addressing issues during scheduled maintenance prevents those roadside shutdowns and keeps freight moving. Tires are the most expensive and most critical wear item on a truck. An 18-wheeler typically runs on 18 tires, and replacing a full set can cost $10,000 or more, depending on tire size and quality. Tires fail for many reasons: underinflation, overloading, road hazards, aging, improper mounting, and simple wear all take their toll. Tire failures are also among the most common causes of roadside breakdowns, making proper tire maintenance both a safety issue and an economic one. The federal government sets minimum tread depth requirements. Steer tires must have at least 4/32 of an inch of tread depth, while drive and trailer tires require 2/32. These are minimums for legal operation, but many fleets replace tires well before they reach these limits, knowing that performance degrades as tread wears. Tire pressure is critical and often neglected. Underinflated tires flex excessively, generating heat that breaks down the rubber and can lead to catastrophic failure. They also increase rolling resistance, reducing fuel economy. Overinflated tires provide a harsh ride and wear unevenly, with the center of the tread wearing faster than the shoulders. The correct inflation pressure depends on the load being carried and is specified by the tire manufacturer for different weight scenarios. A tire's sidewall lists its maximum load and corresponding pressure, but actual operating pressure should match the load and be checked when tires are cold, before the truck has been driven. Heat from driving increases pressure, so measurements taken after highway miles will read higher than true cold pressure. Many progressive fleets use tire pressure monitoring systems that alert drivers to underinflation in real time, preventing damage before it occurs. Tread depth measurement is straightforward with the right tool. A tread depth gauge inserts into the grooves, providing a precise reading in 30 seconds of an inch. For quick checks, the penny test works in a pinch. Insert a penny into the tread groove with Lincoln's head upside down. If you can see the top of Lincoln's head, the tire is worn below minimum legal depth and must be replaced. More sophisticated fleets track tread depth across their tire inventory, rotating tires to even out wear, and pulling tires from service when they approach minimum depths. Some tires have built-in wear bars, small raised sections in the grooves that become visible when the tread wears to minimum depth. Tire rotation extends tire life by distributing wear evenly across all positions. Steer tires wear differently than drive tires, which wear differently than trailer tires. Steer tires experience lateral scrubbing during turns, wearing the shoulders. Drive tires take the torque of acceleration and the scrub of turning, often developing a stepped wear pattern on the edges. Trailer tires follow placidly, often lasting longer than tires in other positions. By rotating tires between positions, fleets maximize the useful life of their tire investment. A typical rotation schedule might move drive tires to trailer positions and trailer tires to drive positions every 60,000 miles, or when tread depth differences become significant. Steer tires are rarely rotated to other positions due to safety concerns and different load ratings. Retreading or recapping tires is common practice in trucking, offering significant cost savings compared to buying new tires. In retreading, the worn tread is ground off down to the casing. The casing is inspected for damage, and new tread rubber is applied and cured onto the tire. A quality retread can provide 80% or more of the life of a new tire at 50% or less of the cost. Steer tires should never be retreaded for safety reasons, but drive and trailer positions are excellent candidates. The key to successful retreading is starting with a quality casing in good condition. Tires that have been run underinflated, overloaded, or with severe impacts may have internal damage that makes them unsuitable for retreading. Retreading is an environmental win as well, keeping tires out of landfills and reducing the petroleum consumption needed to manufacture new tires. Wheel end maintenance goes hand in hand with tire care. The wheel end includes the hub, bearings, seals, and brake components, all of which require periodic service. Wheel bearings should be repacked with grease during brake relines or annually, whichever comes first. Improperly adjusted bearings can cause wheel wobble, uneven tire wear, and in extreme cases, wheel separation. Seals prevent grease from leaking out and contaminants from getting in, and they should be replaced whenever bearings are serviced. Technicians also check wheel studs and nuts for damage, ensuring lug nuts are torqued to specification. A loose wheel is a disaster waiting to happen, potentially leading to wheel separation at highway speeds. Proper torque and regular retorque checks prevent this nightmare scenario. The cooling system keeps the engine from destroying itself with its own heat. Diesel engines run hot, with combustion temperatures exceeding 2,000 degrees Fahrenheit. The cooling system circulates coolant through passages in the engine block and cylinder head, absorbing heat and carrying it to the radiator where airflow dissipates it. A typical truck engine holds 15 to 25 gallons of coolant, a 50-50 mixture of antifreeze and water that resists freezing in winter and boiling in summer. The coolant also contains additives that prevent corrosion, lubricate the water pump, and condition seals. Over time, these additives deplete and the coolant becomes less effective. Most manufacturers recommend changing coolant every 50,000 to 60,000 miles or every 2 years, though extended life coolants can last longer when properly maintained. The water pump circulates coolant through the system, driven by a belt or gear from the engine. It is a simple pump, but when it fails, the consequences are severe. A failed water pump stops coolant circulation, causing the engine to overheat in minutes. Warning signs of impending failure include coolant leaks from the pump's weep hole, a squealing noise from worn bearings, or visible play in the pump shaft. Some technicians check water pump condition during oil changes, looking for excessive shaft movement. Replacing a water pump before it fails is far cheaper and less disruptive than dealing with an overheated engine on the roadside. The radiator is the heat exchanger, using airflow to cool the hot coolant before it cycles back into the engine. Radiator cores are delicate, thin aluminum or copper fins that provide maximum surface area for heat transfer, but are easily damaged by road debris, corrosion, or internal blockage. Radiators should be inspected regularly for fin damage, leaks, and internal deposits. A clogged radiator cannot dissipate heat effectively, leading to overheating even when the coolant level is correct. External cleaning removes bugs, leaves, and dirt that block airflow, while internal flushing removes scale and rust deposits. Pressure testing the radiator cap and cooling system checks for leaks that might not be visible, but allow coolant loss and pressure drop. The thermostat is a valve that controls coolant flow, keeping the engine at optimal operating temperature. When the engine is cold, the thermostat stays closed, blocking coolant flow to the radiator and allowing the engine to warm quickly. As temperature rises, the thermostat opens, allowing coolant to flow through the radiator for cooling. A stuck-closed thermostat causes overheating because coolant cannot reach the radiator. A stuck-open thermostat prevents the engine from reaching proper operating temperature, reducing efficiency and increasing wear. Thermostats are inexpensive and should be replaced as a matter of course during cooling system service, rather than waiting for failure. Coolant hoses are the arteries of the system, carrying hot pressurized coolant between components. Hoses deteriorate over time, weakened by heat cycling, ozone exposure, and chemical attack from the coolant itself. A burst radiator hose can dump the entire cooling system's contents in seconds, leaving you stranded with an overheated engine. Inspecting hoses means looking for cracks, bulges, soft spots, and hardening. Squeeze the hose. It should feel firm but pliable, not rock hard or mushy. Check where hoses attach to fittings, a common failure point. Many fleets replace all cooling system hoses every 3 to 5 years as preventive maintenance, avoiding the risk of roadside failures. Fuel filters are the guardians of the injection system, capturing contaminants before they can damage precision components. Most diesel engines have 2 fuel filters. A primary filter between the tank and the fuel transfer pump captures larger particles and often includes a water separator to remove moisture. A secondary filter between the transfer pump and injection pump or injectors catches finer particles. Diesel fuel systems operate at extremely high pressures, up to 30,000 psi in modern common rail systems. Tiny particles that would be harmless in older engines can damage injector nozzles or score the precision surfaces of injection pumps. Replacing fuel filters every 10,000 to 15,000 miles, or as specified by the manufacturer, is cheap insurance against expensive fuel system repairs. Water in diesel fuel is a perennial problem, especially in humid climates or with improperly maintained bulk storage tanks. Water enters fuel tanks through condensation, contaminated fuel deliveries, or leaking tank seals. It sinks to the bottom of the tank because it is heavier than diesel and can be drawn into the fuel system. Water causes rust, promotes bacterial and fungal growth, and can cause injection system components to seize. The water separator, typically part of the primary fuel filter, catches free water and stores it in a bowl that must be drained regularly. Many trucks have a water and fuel sensor that illuminates a warning light when excessive water accumulates. Draining the water separator should be part of every pre-trip inspection in humid conditions, or whenever the warning light appears. Fuel injection systems have evolved dramatically, becoming more complex and more precise with each generation. Old mechanical injection systems could tolerate dirty fuel and poor maintenance. though they paid the price in reduced performance and black smoke. Modern common rail and electronic unit injector systems demand clean fuel and proper maintenance. Injectors operate at extreme pressures and close tolerances, and contamination can cause them to stick, leak, or fail entirely. Injector replacement or rebuild can cost thousands of dollars. Preventing fuel system problems is far cheaper than fixing them, making regular filter changes and water draining essential practices. Diesel exhaust fluid, or DEF, is a separate fluid system required on most diesel trucks built after 2010. DEF is a mixture of 32.5% high-purity urea and 67.5% deionized water. It is injected into the exhaust stream where it reacts with nitrogen oxides in the selective catalytic reduction system, converting harmful emissions into harmless nitrogen gas and water vapor. The DEF system has its own tank, pump, injector, and sensors. DEF consumption typically runs 2 to 3% of diesel fuel consumption, so a truck burning 100 gallons of diesel might use 2 to 3 gallons of DEF. The system monitors DEF quality and level constantly, and if it detects problems like contamination, low quality, or an empty tank, it will derate the engine, reducing power to as little as 5 miles per hour. This is the system's way of enforcing emissions compliance, and it has caused significant frustration for operators when sensors malfunction or contamination occurs. DEF must be stored properly to maintain its quality. It degrades when exposed to temperatures above 86 degrees Fahrenheit and freezes at 12 degrees. Storing DEF in direct sunlight or extreme heat shortens its useful life. Contamination is the other major concern. Even small amounts of diesel fuel, dirt, or other substances in the DEF tank can damage the injection system and trigger derates. DEF should only be dispensed using dedicated equipment, never shared with diesel fuel lines or storage. Cross-contamination, where diesel fuel accidentally ends up in the DEF tank or vice versa, is catastrophic and requires complete system flushing and often component replacement. DEF quality should meet ISO standard 22241 and carry API certification. Cheap or off-brand DEF can contain impurities that damage the system. The battery provides the initial burst of power needed to crank the engine and supplies electricity when the engine is off. Heavy trucks typically use 1 or 2 large 12-volt batteries wired in parallel for increased cranking capacity. Cold weather is hard on batteries because chemical reactions slow, reducing available power just when cold oil and stiff engine components require more power to turn over. A battery's capacity is rated in cold cranking amps. The current it can deliver at 0 degrees Fahrenheit for 30 seconds while maintaining at least 7.2 volts. Higher CCA ratings mean better cold weather starting. Batteries typically last 3 to 5 years, though lifespan varies with climate, usage patterns, and maintenance. A failing battery shows warning signs: slow cranking, dim lights when starting, and swollen or corroded terminals. Testing battery voltage with a multimeter is simple. A fully charged battery at rest should read 12.6 volts or higher. Anything below 12 volts indicates a discharged battery that may not have enough power to start the engine. The alternator keeps the battery charged and powers the electrical system when the engine runs. It is a generator driven by a belt from the engine, converting mechanical energy into electrical energy. Alternators produce voltage between 13.8 and 14.4 volts when functioning properly, slightly higher than battery voltage to ensure charging occurs. A failing alternator shows itself through a warning light on the dashboard, dimming lights, or a battery that repeatedly goes dead. Alternator problems can stem from worn brushes, damaged diodes, or belt issues. A loose or worn belt slips, preventing the alternator from spinning at the proper speed. A broken belt leaves you running on battery power alone, and you might have as little as 2 hours before the battery is too depleted to keep the engine running. Checking belt condition and tension during routine service prevents this scenario. Wiring in a truck is extensive, miles of copper strands connecting hundreds of components. Wiring failures happen, especially in trucks that experience vibration, temperature extremes, and exposure to moisture. Frayed wires, corroded connections, and chafed insulation all disrupt electrical flow, causing intermittent problems that can be maddeningly difficult to diagnose. During maintenance, technicians look for damaged wiring, especially in areas exposed to heat, moving parts, or road spray. Protecting wiring with proper looms and grommets prevents many problems. When electrical gremlins appear, intermittent failures that defy logic, the culprit is often a wiring issue. Finding it requires patience, a wiring diagram, and a methodical approach to testing circuits and connections. Fuses and relays protect electrical circuits from overloads. Fuses are sacrificial devices that burn out if too much current flows, breaking the circuit before wiring or components can be damaged. Relays are electrically operated switches that allow low-current circuits to control high-current devices. A fuse that blows repeatedly indicates a problem in that circuit, not a problem with the fuse. Replacing the fuse without finding and fixing the underlying issue just means you will be replacing it again. Keeping spare fuses of the correct amperage rating in the truck is wise, allowing quick replacement when a fuse blows. Relays can also fail, either sticking open so a circuit never energizes or sticking closed so a circuit stays energized constantly. Diagnosing relay problems requires a test light or multimeter and knowledge of how the circuit should function. Transmission fluid lubricates gears, clutches, and bearings while providing hydraulic pressure for shifting. In manual transmissions, the fluid's job is purely lubrication and cooling. In automated manual or automatic transmissions, it also serves as the hydraulic medium that engages clutches and operates shift mechanisms. Transmission fluid should be checked periodically and changed according to manufacturer specifications, typically every 50,000 to 100,000 miles depending on application. Fluid that smells burnt, appears dark, or contains metal particles indicates transmission problems. Burnt smell suggests overheating, dark color means the fluid is breaking down, and metal particles reveal wear on gears or bearings. Addressing these symptoms early prevents major transmission failures that can cost $10,000 or more. The differential transfers power from the drive shaft to the axle shafts, allowing the wheels to rotate at different speeds during turns. Differentials use heavy gears bathed in thick oil to handle the enormous torque from the engine. That gear oil must be changed periodically, typically every 100,000 miles, though severe service applications require more frequent changes. Differential oil darkens with use as it suspends tiny metal particles from gear wear. Checking the oil level is simple with a fill plug on the differential housing. The level should be at the bottom of the fill hole. Low oil levels can cause differential damage, while overfilling can lead to seal failure and leaks. Metal particles on the magnetic drain plug are normal to a degree, but excessive buildup suggests where that needs attention. U-joints connect sections of the drive shaft, allowing it to transmit power while accommodating angle changes and suspension movement. U-joints wear over time, and when they fail, the results can be catastrophic. A failed U-joint on the drive shaft can allow the drive shaft to drop and strike the road, potentially damaging the underside of the truck, or even vaulting the truck if the drive shaft digs in. U-joints should be greased regularly if they have grease fittings, and inspected for play, rust, and damaged seals. Testing involves grabbing the drive shaft and trying to move it. Any clunking or visible movement indicates worn joints that need replacement. Some modern U-joints are sealed and require no greasing, but they still need regular inspection. Clutches in manual transmission trucks are wear items, gradually degrading with every start from a stop. Clutch life depends on driving style, load, terrain, and adjustment. A driver who eases the clutch in gently and avoids slipping it unnecessarily might get 500,000 miles from a clutch. Another driver with poor technique might need replacement at 200,000 miles. Signs of clutch wear include slipping under load, difficulty shifting, and a changing engagement point. The clutch pedals feel changes as the clutch wears, often becoming softer and engaging higher in the pedal travel. Adjusting clutch-free play, the amount of pedal movement before the clutch begins to disengage, is a regular maintenance task that keeps shifting smooth and prevents premature wear. The air filter prevents dirt, dust, and debris from entering the engine, protecting cylinders, pistons, and turbochargers from abrasive damage. Even microscopic particles can cause wear if they enter the combustion chamber, so filtration is critical. Most heavy trucks use large cylindrical or panel air filters that can capture particles as small as 5 microns. The filter works by forcing air through a pleated paper or synthetic media that traps contaminants. As the filter loads with dirt, airflow restriction increases, reducing engine performance and fuel economy. A dirty air filter can rob an engine of horsepower and increase fuel consumption by several percentage points. Most manufacturers recommend replacing the air filter annually or every 50,000 miles, though trucks operating in dusty environments may need more frequent changes. Some trucks have air filter restriction gauges that indicate when the filter needs replacement based on actual restriction rather than time or mileage. The turbocharger forces more air into the engine than atmospheric pressure alone would allow, increasing power output without increasing engine size. Turbos spin at tremendous speeds, often exceeding 100,000 RPM, supported by tiny oil-lubricated bearings. These bearings depend on clean, properly pressurized oil for survival. Dirty oil or low oil pressure can destroy a turbo in minutes. Many turbo failures are caused by oil contamination or oil starvation, making regular oil changes and proper oil level critical to turbo life. Turbos also generate significant heat, with exhaust side temperatures exceeding 1,000 degrees Fahrenheit. After a hard run, shutting the engine off immediately can cause coking, where oil in the hot turbo bearing area carbonizes and forms deposits. Allowing the engine to idle for a few minutes before shutdown lets the turbo cool gradually, protecting the bearings. The intercooler cools the compressed air from the turbocharger before it enters the engine. Compressing air heats it, and hot air is less dense than cool air, containing fewer oxygen molecules per volume. By cooling the compressed air, the intercooler increases its density, allowing more oxygen into the cylinders for more complete combustion and greater power. Intercoolers use either air-to-air heat exchangers, where ram air cools the compressed charge air, or air-to-water exchangers that circulate coolant through the intercooler core. Air-to-air intercoolers are simpler and more common, mounted in front of the radiator where they receive maximum airflow. Keeping the intercooler clean externally and internally is important for efficiency. External debris blocks airflow, while internal oil deposits from worn turbo seals reduce cooling capacity. Truck suspension systems balance ride quality, load capacity, and handling. Most trucks use leaf springs or air springs to support the chassis and absorb road shocks. Leaf springs are stacks of curved steel plates that flex to absorb bumps, traditional, durable, and relatively maintenance-free. Air springs use rubber bellows filled with compressed air, providing a smoother ride and the ability to adjust ride height. Both systems require periodic inspection for wear and damage. Leaf spring bushings wear over time, creating looseness that affects handling and causes uneven tire wear. Air springs can develop leaks, cracks, or tears that cause the truck to sag on one side. Replacing worn suspension components improves ride quality, reduces driver fatigue, and prevents secondary damage to the frame and other components. Shock absorbers dampen spring oscillations, preventing the truck from bouncing excessively after hitting a bump. Worn shocks allow prolonged bouncing, reducing tire contact with the road and affecting braking and handling. Testing shocks involves a bounce test, pushing down hard on a corner of the truck and then releasing. The truck should return to level and stop moving. If it bounces more than once or twice, the shocks are worn. Leaking fluid from shock bodies is another clear sign of failure. Replacing shocks is straightforward, and new shocks dramatically improve ride quality and handling on trucks where the originals have worn out. Lighting systems keep trucks visible to other drivers and allow drivers to see the road ahead. Federal regulations specify minimum lighting requirements, including headlights, tail lights, brake lights, turn signals, clearance lights, and marker lights. Keeping all lights functioning is not just a safety issue but a legal one. Roadside inspections check lighting, and non-functional lights can result in violations and fines. LED lights have largely replaced incandescent bulbs in modern trucks, offering brighter light, longer lifespan, and lower power consumption. An LED marker light might last 100,000 hours compared to a few thousand for an incandescent bulb. The initial cost is higher, but the reduced maintenance and improved reliability make LEDs the preferred choice. Windshield wipers are often overlooked until they are needed in a rainstorm. Worn wiper blades leave streaks, chatter across the glass, or miss sections entirely, compromising visibility. Wiper blades should be replaced at least annually, more often if they show signs of cracking, splitting, or tearing. Windshield washer fluid should be checked regularly and filled with a quality solution that cleans effectively and resists freezing in winter. Running out of washer fluid when you need to clean road spray or bug splatter from the windshield can be more than an inconvenience. It can be a safety hazard. Mirrors are the truck driver's eyes on the world behind and beside the truck. Properly adjusted mirrors eliminate blind spots and allow the driver to monitor traffic, check tire condition, and watch for issues. Keeping mirrors clean and intact is basic but essential maintenance. A broken or missing mirror is a serious safety violation and will result in the truck being placed out of service during a roadside inspection. Drive belts transfer power from the engine to accessories like the alternator, air compressor, power steering pump, and water pump. Most modern trucks use a single serpentine belt that snakes around multiple pulleys, driven by the crankshaft. This belt is critical. If it breaks, you lose multiple systems simultaneously, potentially stranding you. Belts wear over time, developing cracks, fraying, or glazing. Inspecting belt condition means looking for these signs and checking tension. A loose belt slips, squeals, and fails to drive accessories properly. An over-tightened belt puts stress on bearings in the pulleys and can cause premature failure. Belt tensioners maintain proper tension automatically but can wear out, allowing slack to develop. Replacing belts before they fail, typically every 100,000 miles or when signs of wear appear, prevents breakdowns. The frame is the backbone of the truck, supporting the engine, transmission, suspension, and cab. Frame cracks can develop from stress, corrosion, or impact damage. Small cracks can grow into major failures if not caught and repaired. Frame inspections look for cracks, especially at stress points like where cross members attach or where the fifth wheel is mounted. Rust weakens the frame, and trucks operating in areas with heavy salt use in winter are particularly susceptible. Protective coatings and regular washing help prevent corrosion. Repairing a cracked frame usually involves welding and reinforcement plates, or sometimes replacing sections. Work that must be done by qualified welders to maintain structural integrity. The exhaust system routes hot combustion gases away from the engine, reduces noise through mufflers, and treats emissions through the diesel particulate filter and selective catalytic reduction system. Exhaust leaks are more than annoying noise. They can allow toxic gases to enter the cab and reduce the efficiency of emission systems. Inspecting exhaust components means looking for rust, cracks, and loose connections. The diesel particulate filter captures soot from the exhaust, storing it until a regeneration cycle burns it away at high temperatures. DPF maintenance involves monitoring for excessive soot accumulation and performing forced regenerations or cleanings when necessary. A clogged DPF restricts exhaust flow, reducing power and fuel economy. Before every trip, drivers are required by law to conduct a pre-trip inspection, a systematic walk-around checking key systems and components. This inspection catches problems before they become roadside emergencies, checking tire condition and pressure, light function, brake adjustment, fluid levels, hose condition, and more. A thorough pre-trip inspection takes 15 to 20 minutes and can prevent hours of delay and thousands in repair costs. It is the first line of defense in maintenance, catching issues early when they are cheap and easy to fix. Post-trip inspections are equally important, looking for problems that develop during the day's work. Any defects found during pre-trip or post-trip inspections must be documented on a driver vehicle inspection report. The motor carrier must review these reports and ensure repairs are made before the vehicle is dispatched again. This paper trail creates accountability and ensures problems do not slip through the cracks. Preventive maintenance is the philosophy of servicing components before they fail, based on time, mileage, or operating hours. A well-designed PM schedule considers manufacturer recommendations, operating conditions, and the truck's specific use. Typical intervals include daily checks by drivers, service every 10,000 to 15,000 miles for oil changes and inspections, and major services every 50,000 to 100,000 miles for transmission service, coolant changes, and comprehensive inspections. Fleets that stick to rigorous PM schedules experience fewer breakdowns, lower repair costs, and longer vehicle life compared to those that defer maintenance or operate on a run-to-failure philosophy. Detailed maintenance records document every service, repair, and inspection performed on a truck. These records serve multiple purposes. They help technicians diagnose problems by showing maintenance history. They prove compliance with regulations during audits. They increase resale value by demonstrating the truck was well maintained. They help identify patterns, like recurring failures of a particular component. Modern fleet management software digitizes these records, tracking maintenance costs per mile, alerting when service is due, and analyzing data to optimize maintenance schedules. Drivers are the front line of maintenance, the people who spend the most time with the truck and notice when something changes. An attentive driver hears the new noise, feels the different vibration, sees the leak or the light. Training drivers to recognize warning signs and report them promptly prevents many major failures. A driver who ignores a small oil leak or a squealing belt is inviting a breakdown. A driver who reports these issues immediately allows the fleet to schedule repairs before they become emergencies. Maintenance costs money, but deferred maintenance costs far more. Oil changes are cheap compared to engine rebuilds. Brake linings are inexpensive compared to the costs of an accident caused by brake failure. PM schedules and proactive component replacement are investments that pay dividends in uptime, fuel economy, and equipment lifespan. Fleets track cost per mile for maintenance, comparing it against industry benchmarks and analyzing where money is spent. This data-driven approach optimizes maintenance strategies, identifying where increased preventive maintenance reduces overall costs. Truck maintenance is evolving with technology. Telematics systems monitor truck performance in real time, alerting fleets to problems before they cause breakdowns. Predictive analytics use data to forecast component failures, scheduling maintenance just in time rather than on fixed intervals. Electric trucks are beginning to enter fleets, bringing different maintenance needs, Fewer fluids to change, but new battery and electrical systems to service. Autonomous trucks, still largely in testing, will change how maintenance is scheduled and performed. Through all these changes, the fundamental truth remains. These machines must be maintained. Their complexity may evolve, but the need for care, inspection, and timely repair continues. And so we reach the end of our journey through the world of truck maintenance. From oil that lubricates to air that brakes, from filters that protect to lights that guide, we have wandered through the systems and components that keep trucks moving. Every truck tells a story through its maintenance history, a narrative of care or neglect, of proactive service or deferred problems. The trucks that last longest, that deliver most reliably, that cost least to operate are almost always the ones that receive consistent, thoughtful maintenance. They are machines, yes, but machines that respond to care, that reward attention, that repay investment in longer service and fewer failures. If you have found value in this exploration, consider subscribing to join us on future rides down America's highways. Leave a comment sharing your own maintenance experiences, your victories, and your hard-learned lessons. And remember, the road is only as reliable as the machine that carries you across it. Maintain that machine, respect its needs, understand its language of sounds and smells and vibrations. It will speak to you if you listen. It will serve you faithfully if you care for it. For now, let this settle into your thoughts like dust on a summer highway. Imagine the rhythm of maintenance schedules, the satisfaction of a job done right, the peace of mind that comes from knowing your truck is ready. And when you see a big rig rolling down the interstate, know that somewhere in its recent past, a technician changed its oil, a driver checked its tires, a mechanic adjusted its brakes. Know that it carries not just freight but a history of care, a chain of decisions that keep it moving safely and reliably. Good night, and may your rigs run strong and your maintenance schedule stay current.